And now in this lecture I'll answer two questions. In the first question you find out the radius of this circle that blocks quadrilateral ABCD. And in the second question you find out the length of this line segment AP is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have quadrilateral ABCD that is inscribed by this circle. We know that side AB of quadrilateral ABCD equals to side BC. We know that the diameter of this circle is AC is the diameter of the circle, chord AC is the diameter of the circle. We also know that the perimeter of this quadrilateral ABCD is equal to 18 units in its length. That is to say, the sum of its four side lengths, in total it is equal to 18. AB plus BC plus CD plus DA equals to 18 units. We also know that the area of this quadrilateral ABCD is equal to 16 units in its size. Again, our task is to find out the radius of this circle. So, first of all, we define the sides of this quadrilateral ABCD with letters. We define the length of side AB as A. That is to say, side AB equals to A units in its length. Because of the fact that AB equals to BC in its length, it means that BC must be also equal to A. We define the length of side AD as B, and the length of this side CD as C. So here you can implement rule 7. I'm going to implement rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ECB that subtend on chord AB, that is the diameter of this circle, and therefore it is equal to 90 degrees in its size. So according to this rule 7, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So in the drawing, we have peripheral angle ABC that subtend on chord AC, that is the diameter of the circle, and therefore peripheral angle ABC must be equal to 90 degrees in its size according to rule 7. Likewise, this is peripheral angle CDA that also subtend on chord AC, that is the diameter of this circle, and therefore according to rule 7, it must be equal to 90 degrees in its size. In the next step, we implement the Pythagoras theorem on both those two right angles, on this right triangle ABC and on this right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression of Pythagoras theorem. So in this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, according to the Pythagoras theorem, this right triangle ABC AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is AC squared equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, we should find out that AC squared equals to A squared plus A squared, that is 2A squared. So according to equation 1, AC squared equals to 2A squared. In the next step, we implement the Pythagoras theorem on this right triangle, triangle ADC. This right triangle ADC. Here by PT is evaluation for Pythagoras theorem. So on this right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus CD squared. AC is the missing side, so it is AC squared equals to AD squared. AD is B, therefore AD squared is B squared plus CD squared. CD is C, therefore CD squared is C squared. So in total, according to equation 2, we should find out that AC squared equals to B squared plus C squared. Well, according to equation 1, we already found out that AC squared equals to 2A squared. So we have two different equations for AC squared. So therefore, we get equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. And again, according to equation 3, AC squared according to equation 1 must be equal to AC squared according to equation 2. So AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2, that equals to B squared plus C squared. So in total, according to equation 3, I should find out that 2A squared equals to B squared plus C squared. So here we divide this equation 3 by 2 and find that A squared equals to B squared plus C squared over 2. The perimeter of this quadrilateral ABCD is equal to 18. That is to say, AB plus BC plus CD plus DA equals to 18. AB is A, BC is also A, CD is C, and DA is B. So in total, A plus A is 2A, plus C plus B equals to 18. 2A plus C plus B equals to 18. So A plus B plus C equals to 18. This is according to equation 4. According to what is given as the equation, the area of this quadrilateral ABCD equals to 16 square units in size. Quadrilateral ABCD consists of those two shapes. Therefore, the area of quadrilateral ABCD must be equal to the sum of the areas of those two shapes that it consists of. This is to say, the area of quadrilateral ABCD in total must be equal to the area of the first shape that is consisted of the area of this right triangle ABC plus the area of the second shape that is consisted of the area of this right triangle ADC. And again, the area of polygonal ABCD, in total, must be equal to the sum of the areas of the two shapes that it consists of. The area of the shape that is the area of the right triangle ABC plus the area of the second shape that is the area of the right triangle ADC. It's given us a question that the area of polygonal ABCD equals to 16 square units in size. Therefore, we substitute the area of polygonal ABCD by 16. And it equals to the area of the right triangle ABC. What is the area of this right triangle ABC? The area of the right triangle ABC equals to the base AB times the height BC over 2. AB is A, BC is A, so divided by 2. So it is A times A over 2. A times A is A square, so it is A square over 2. So in total, the area of the right triangle ABC is equals to A square over 2 square units in size. Plus the area of this right triangle ADC. It is equals to the base AD times the height DC over 2. AD is B, DC is C, therefore it is equals to BC over 2. Of the second job, it is equals to B times C over 2 square units in size. So in total we should find out that 16 equals to A square over 2 plus BC over 2. So here we multiply this equation 5 by 2 and finally is according to equation 5. $32 equals to A square over 2 times 2 is A square plus BC over 2 times 2 is BC. So in total we should find out that according to equation 5, $32 equals to A square plus BC. According to equation 3, we only found out that A square equals to B square plus C square over 2. So we can substitute A square in this equation 5 by B square plus C square over 2 for this equation 3. We will do it all, we get that 32 equals to A square is B square plus C square over 2 plus BC. So and total according to equation 5, we have found out that 32 equals to B square plus C square over 2 plus B times C. Here we multiply BC by 2 and then we divide it by 2 in order to overcome part of this expression, and we get that in total 32 according to equation 5, 32 equals to B square plus C square over 2. Here we multiply BC by 2, so it is 2 times BC, and then we divide it by 2, so we change nothing. So in total we should find out that 32 equals to B square plus C square plus 2 times 3 times C over 2. Here we multiply this equation 5 by 2, and finally get that according to equation 5, 32 times 2 is 64 equals to B square plus C square plus 2 times B times C. So here we use the algebraic identity. It says that A square plus B square plus 2 times A times B equals to A plus B square. According to this algebraic identity, we get that B square plus C square plus 2 times B times C equals to b plus c square, and it is equals to 64. So total according to equation 5, we have found out that b plus c square equals to 64. So here we take out all the equation, and finally get that according to equation 5, b plus c square is b plus c equals to the square root of 64 is 8. The square root of 64 is 8. So total according to equation 5, we have found out that b plus c equals to 8. Well, according to equation 4, we already found out that two a plus b plus c equals to 18. And again, according to equation 4, we already found out that 2a plus b plus c equals to 18, but b plus c equals to 8, according to equation 5. So let's solve b plus c in this equation 4 by 8 from equation 5. We do it now, we get it according to equation 4. 2a in b plus c is 8, so it is plus 8 equals to 18. So in total, according to equation 4, we found out that 2a plus 8 equals to 18. Here we subtract 8 for this equation 4, and finally get it according to equation 4. 2a equals to 18 minus 8 is 10, so 2a equals to 10. Here we divide this equation by 2, equation 4 by 2, and finally get it, and we get that a equals to 10 over 2 is 5. A equals to 5 units in Islam. This is side AB, equals to n equals to 5, so AB equals to 5. Likewise, this is side BC, it also equals to A, and A equals to 5, and therefore BC also equals to 5. So in the next step, we'll implement the Pythagoras theorem on this right triangle, triangle ABC. Here by PT is the equation for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle ABC, AC squared is the square of the hypotenuse equals to AB squared plus BC squared. Again, according to the Pythagoras theorem, on this right triangle ABC, AC squared is the square of the hypotenuse equals to AB squared plus BC squared. AC is the missing side, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So I should found out that A squared, which is the square of the hypotenuse, equals to 25 plus 25, that is 50. AC squared equals to 50. Here we substitute 50 by 25 times 2. So in total we get that AC squared equals to 25 times 2. Here we take out all the equation and finally get that AC equals to the square root of 25 is 5, so inside the order of only with 2. So to that, we can find out that AC equals to 5 times square root of 2 units in its length. AC is the diameter of this circle. That is equals to 5 times square root of 2. Therefore, the radius must be equal to half of the diameter AC. So the radius R of the circle, that is the radius that we are looking for in this question, must be equal to the diameter AC over 2. This is to say it is 5 times square root of 2 over 2. So the radius R of the circle, that is the radius that we are looking for, it is equal to either 5 times square root of 2 over 2 units in itself. Therefore, in terms of numbers, it is equal to 3.536 units in its length. And again, if we found out that the radius that we are looking for in this question, the radius of this circle, it is equal to either 5 times square root of 2 over 2 units in itself, or in terms of numbers, the radius R of this circle, it is equal to 3.536 units in its length. So we finish with the first question. In the next step, I will present you the second question, and then we solve the second question of this section. In this second question, our task is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is inscribed by this right angle ABC. This is angle ABC, this is the right angle. We also know that QS equals to 25 units in its length, chord PQ equals to 24 units in its length. This is tangent to this circle at this point, so we define the point of tendency of this tangent with this circle. This point is point M. So SM is the tangent to this circle at point M. Again, our test is to find out the length of this line segment AP equals to x. We have to find out the value of x. So first of all, we can implement rule 2 in our drawing. So since we can rule 2, according to rule 2, the lengths of two tangents from a current point to a circle are equal. So in the drawing, we have a circle, this is the current point P. On this current point P, we have two tangents to this circle, tangent PA and tangent PB. According to rule 2, they are equal to each other. This is to say the length of tangent PA equals to the length of tangent PB, or PA equals to PB. So we can finish with rule 2 in our drawing. Now, because in our drawing, we have this is the current point A. From this current point A, we have two tangents to this circle, tangent AP and tangent AQ. According to rule 2, they are equal to each other. This is to say AP equals to AQ. But AP equals to x, therefore AQ must be also equal to x units in its length. We find the length from this short tangent BM as A. And we focus on this current point B. From this current point B, we have two tangents to this circle, tangent BM and tangent BQ. And from this all two, they are equal to each other. This is to say BM equals to BQ. BM equals to BQ, but BM equals to A, therefore BQ must be also equal to A units in its length. So in the next step, we focus on this current point S. On this current point S, we have tangent SM, this is tangent to this circle at point M. Likewise, we have chord PQ, the extended chord PQ touches point S. So all the requirements for 10 are satisfied, and therefore we can implement here all 10. according to Olympiad. Olympiad is for in any circle. In any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true. PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So, in the drawing, we have a circle. This is the connection point P. From this connection point P, we have tangent PT, that is tangent to the circle point T. Likewise, we have chord BA, the extended chord BA, touches point P. So in this, this whole ultimate, the following equation in our drawing is so that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So we can implement ultimate point S, or we have tangent SM, that is tangent to the second point M. And likewise, extended chord PQ touches point S. So all the requirements of Olympiad are satisfied, and therefore can implement Olympiad. According to Olympiad, the following equation is true: that SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. So write it down. And again, according to Olympiad, if you follow the common start point S, the following equation is true. That SM squared equals to SQ times SP. SM is the missing tangent, so whatever this it is, so it is SM squared equals to SQ is 25, times SP total equals to SQ that is 25, plus QP that is 24. So in total, SP equals to 25 plus 24, that is 49. So in total, if you have unloaded SM squared equals to 25 plus 49. Here you take out all the equation, and get this SM equals to the square root of 25 is 5, and the square root of 49 is 7. So in total, SM equals to 5 times 7, that is 35. So then SM equals to 45 minutes in this line. This is tangent SM equals to 45 minutes in this line. What is the left for this is in line 7 SB. From the line it is very interesting that SB in total equals to SM must be M. So I don't know. SB in total equals to SM must be M. SB equals to SM, that is 35, plus BM, that is 8. So in total, SB equals to 35 minus units in SM. SM is a tangent to the second point M, so SM is a tangent to the absolute straight line. So if we focus on the upper side of the straight line SM at point B, if the sum of the areas must be equal to 180 degrees according to Wolffish. Wolffish said that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have the upper side of the straight line SM at point B, we have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to Wolffish. Therefore this missing angle must be equal to 90 degrees inside. In the next step, we implement the Pythagoras theorem on this right triangle QSB. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares for the perpendiculars. Here by PT is the version for Pythagoras theorem. So according to the Pythagoras theorem, this gamma times QSB, QS squared, that is the square of the hypotenuse, is equal to QB squared plus SB squared. And again, the right angle QSB according to the Pythagoras theorem. QS squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. QS is 25, therefore QS squared is 25 squared, that is 625. And it is equals to QB squared. QB is 8, therefore QB squared is 8 squared. Plus SB squared. SB is 35 minus 8, therefore SB squared is 35 minus 8 squared. So in total, if you download it, 625 equals to 8 squared plus 35 minus 8 squared. So 625 equals to 8 squared plus 35 minus 8 squared. 35 minus 8 squared equals to 35 squared, that is 1225, plus 8 squared, minus 35 times 8, that is 178. So in total, 625 equals to 8 squared plus 8 squared is 2 squared, 178 plus 1225. Here we subtract 625 from this equation and get it here we left with nothing, that is to say 0, while on the other side of the equation we have 2a squared, 178 plus 1225. 1225 from 625 is 600. So then if you found out the 0 equals to 2a squared, 178 plus 600. Here we divide this equation by 2. And finally we get that 2a squared over 2 is a squared. 178 over 2 is 145a. And finally 600 over 2 is 300. And 0 over 2 is 0. So actually this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of a according to the following formula. Find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared plus 4 times a times c. Divided by 2a again. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2. Now a specific quadratic equation, that is to say a squared plus 45a plus 100 equals to 0. The variable that we are looking for is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 45. And finally, the coefficient c equals to 300. So we put the data for specific quadratic equation in this general formula for x, and this way we find out the value of the values of a, because x equals to a. So we do it now and get that a equals to minus b. B is minus 45, therefore minus b is plus 35. And here plus minus square root of b squared. B is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a times c. A is 1, c is 300, so minus 4 times a times 1 is minus 4 times 300, that is minus 1200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, if you found out that x equals to 35 plus minus square root of 225 plus 1200, 1225 plus 1200. So a equals to 35 plus minus 1225 plus 1200 is 25 over 2. So a equals to 35 plus minus 4 to 5 over 2. And a equals to 35 plus minus 1225 minus 1200 is 25 over 2. So A equals to 35. A equals to 35 plus minus the square root of 25 is 5 over 2. Okay, again, I should hold on that equals to 45 plus minus 5 over 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 40. 40 over 2 is 12. 40 over 2 is 20. So according to the first solution, for A that A equals to 20. And also a second solution for A. The second solution for A is that A equals to 35 plus 5 over 2. 35 plus 5 is 30. 30 over 2 is 15. So the second solution for A is A equals to 15. And the first solution is that A equals to 20. In the next step, we do a construction. But before that, we have here a triangle AQP. This triangle AQP is an associated triangle because side AQ equals to side AP. QP is the base of the associated triangle AQP. So in the next step, we will do a construction. That is to say, from the vertex A, we will do perpendicular on the base QP. Again, from vertex A, we will do perpendicular on the base QP. Actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A, the base QP. This point is point Z. So we have here an associated triangle AQP, and also perpendicular AZ on the base QP. So we can implement here rule 21. Repeat figure rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisects the base. So in the drawing, we have the associated triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC. So on this side AQM, we go perpendicular AO to the base BC. And according to this one, or 21, the perpendicular AO to the base BC by second the base BC. That is to say, divide the base BC into two halves. The first half BQ, of course, must be equal to the sum of QC. And each half must be equal to BCO2. So BO equals to OC equals to BCO2. We can actually implement Rule 31 in our drawing. Because in our drawing, we have the perpendicular AZ to the base QC of the associated target triangle AQP. According to Rule 21, the perpendicular AZ bisects the base QP. So the first half is QZ, and it is of course must be equal to the second half ZP, and each half must be equal to QP over 2. So I did not. According to Rule 21, the perpendicular AZ bisects the base QP, that is to say QZ equals to ZP. And each half equals to QP over 2. And again, the perpendicular AZ bisects the base QP. So the first half QZ must be equal to the second half ZP, and each half must be equal to QP over 2. QP is 24, therefore QP over 2 is 24 over 2. This is 12. And for this equation, we know that QZ equals to ZP equals to 12. QZ equals to ZP equals to 12. So here QZ equals to 12. And ZP also equals to 12. Those two angles are defined as vertical angles, and vertical angles are equal to each other. So if we define the size of one angle as alpha, then this angle must also equal to alpha. So in this integral EQZ, this angle equals to alpha, this angle equals to 90 degrees. Therefore this first angle must equal to 90 degrees minus alpha. 5 plus 90 degrees minus alpha plus alpha is 90 degrees. 90 degrees plus 90 degrees is equal to 180 degrees. This is the sum of the angles in the triangle. Likewise, in this small green triangle QSB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must equal to 90 degrees minus alpha. According to the symbol, that said that the sum of the angles in a triangle is equal to 180 degrees. This is the triangle AQZ that is similar to this and small triangle QBS. What those two triangles are similar to each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees also, and therefore they are equal to each other. So if you found out that all the figures of this right triangle QSP are corresponding equal to all the figures of this right triangle AQZ, and therefore those two right triangles are similar to each other according to again similarity rule. So write it down. Actually, I found out that the right triangle QBS, the right green triangle, is similar to this right triangle AQZ. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side QS of this triangle QPS or side AQ of this right triangle AQZ is equal to side QB of this small triangle QBS or side QZ of this right triangle AQZ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side US of the small right triangle QBS or side AQ of the big right triangle AQZ is equal to side QB of the small right triangle ABQ or side QZ of the small right triangle AQZ. QS is 25 over AQ is X and it is equals to QB is A or QZ is 12. And actually found out that 25 over X equals to A over 12. E will equals to multiply this equation and finally get that A times X equals to 25 times 12, that is 300. So AX equals to 300. Here we divide this equation by 2 and finally get divide this equation by A and finally get that X equals to 300 over A calculation, we found out that A would be equal to either 20 or 15. In order to find out what is the real value of A, or maybe it has two solutions, it is also possible. So I copied this right triangle ABC with its circle that is inscribed inside it in a new drawing, and we analyze the new drawing in order to find out what is the real value of A. Okay, this is right triangle ABC with its circle that is inscribed inside it, that I copied from the original drawing. We already found out that QB equals to A and AQ equals to X. So in the next step, we find the point of tendency of tangent BC with this circle. This point is point M. We define the center of this circle. This point is point O. We define the radius of this circle as R. In the next step, we join points O and M together with a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, that is equals to R. The radius OM is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. Remember, your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO according to 1. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, this angle also equals to 90 degrees according to 1. Point Q is the point of tendency of tangent AB with this circle. So in the next step, we join points O and Q together by a straight line. OQ is of course the radius of this circle, that is equals to R. And according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in this smooth quadrilateral Q, O, and B, we have 1, 2 ferratagas. We have 1, 2 ferratagas, and therefore this fourth missing angle must be also equal to 90 degrees inside, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral QOBM is 400 degrees, and therefore can write to quadrilateral QOBM is 30 degrees. But we also know that the opposite sides of a rectangle are equal to each other. So in this small rectangle QO and B side, OM must be equal to the opposite side QB, but OM is out, therefore the opposite side QB must be also equal to R in this term. Therefore, R equals to A equals to QB. In the next step, we did another construction, that is to say, we'll extend the radius MQ, the radius MO by a straight line until it touches the circle. We define the touching point of the extended radius with the circle. This point is point Z. OM is a radius, therefore it is a straight line. When you extend a straight line by a straight line, the result MZ must be also a straight line. So if you focus on the right side of the straight line, ZM at point O, give the sum of the areas must be equal to 180 degrees according to rule 3. So which areas we have the right side of ZM at point O, we have this angle that is right angle plus this missing angle, in total must be equal to 180 degrees according to rule 3, therefore this missing angle must be equal to 90 degrees in size. The next step, we do another construction, that is 3 from the side AB. We draw a tangent to the circle that will be tangent at point Z. Again, from AB we draw a tangent to the circle that will be tangent to it at point Z. And we define the touching point of this tangent with this circle. This point is point T. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle, and it is equal to R units in itself. The radius OZ is equal to R, the radius OZ is 1 to point Z, that is the point of tendency of tangent TZ with this circle. And now your radius is 1 to the point of tendency, then tangent TZ will be perpendicular to the radius Z. If TZ is perpendicular to Z, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in total, in the small upper quadrilateral T, Z, or Q, we have 1, 2, 3 angles. And therefore this fourth missing angle is equal to 90 degrees in size. So in quadrilateral T, Z, or Q, we have 4 angles, and therefore relate to quadrilateral T, Z, or Q is a right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So in the small of the TZ or Q, side ZO must be equal to the opposite side TQ. But ZO is out, therefore the opposite side TQ must be also equal to R units in this scenario. We have here, we already found out that QB equals to A equals to R. So QB equals to A and QB also equals to R. What about line 7 AQ? AQ from one side equals to X, but AQ also equals to AT plus TQ. TQ is out, therefore AQ in total equals to AT plus R. So from one side, AQ actually equals to X, but AQ also equals to AT plus R. Again, AQ also equals to AT plus R. It consists of 2 line segments. So AQ also equals to AT plus R. AT is this is side of AT. AT is the side SLF, it is absolutely a positive number. Therefore, AT plus R must be greater than R itself because AT is a positive number. Again, AT plus R must be greater than R because AT is a positive number. And from this non-inequality, we derive that A is smaller than X. A is smaller than X, or X is greater than A. We just right now found out that X is greater than A, We have two solutions that are possible for A. A will be equal to 15, or A also will be equal to 20. And we already found out that x equals to 300 over A. If A equals to 20, then x must be equal to 300 over 20, that is 15. So if A equals to 20, then x must be equal to 15 according to this equation. Likewise, if A equals to 15, then x must be equal to 300 over 15, that is 20. And again, if A equals to 15, then x must be equal to 20. So here, x equals to 15. 15 is definitely smaller than 20, and 20 equals to A. 20 equals to A. From this inequality, we derive that x is less than A. X is smaller than A. X is smaller than A. It contradicts our previous findings that x must be greater than A. If x must be greater than A, x cannot be smaller than A. So due to this contradiction, we present this solution, A can never be equal to 20. And we will take into account only the second solution for A, that A equals to 15, and then x equals to 20. So A equals to 15. 15 is definitely smaller than 20, and 20 equals to x. And from this inequality, A equals to 15 is smaller than 20, is equals to x. We derive that A is less than x. A is smaller than x. A is smaller than x, or x is greater than A. Exactly like our previous one, that x must be greater than A, and x must be greater than A. So the answer to the question is that AP is equals to x is equal to 20 units in its length. And again, if we found out that this is the answer that AP is equals to x, and x equals to 20 units in its length. So we finished to answer the second question. In the next step of some of the lecture, we start with the repetition on the first question, and then repeat on the solution of the second question. this first question, our task is to find out the radius of this circle. So in the drawing we have quadrangle ABCD that is inscribed by this circle. We know that AC is the diameter of this circle. We know that side AB of quadrangle ABCD equals to side BC. We also know that the perimeter of this quadrangle ABCD is equal to 18 units. So the sum of its four side lengths in total it is equals to 18. That is to say AB plus BC plus CD plus DA equals to 18. In addition, we know that the area of this quadrangle ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle that blocks quadrangle ABCD. So first of all, we define the size of quadrangle ABCD with letters. We define the length of side AB as A because of the fact that AB equals to BC in its length, therefore BC must be also equal to A units. We define the length of side AD as B, and we define the length of side CD as C. The next step, we implemented all 7 in our drawing. Investigation on all 7. According to all 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle, and therefore, according to this rule, all 7 peripheral angle ACB must be equal to 90 degrees in its size. So according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So we can implement now drawing rule 7. We have peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size according to rule 7. Likewise, we have peripheral angle ADC that also subtends on chord AC, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its size according to rule 7. The next step, we implement the Pythagoras theorem on those two right angles, the right angle ABC and this right angle ADC. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in the right angle ABC, it means that AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Repeat again, the right angle ABC. According to the Pythagoras theorem, we get that AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared according to this equation, equation 1. In the next step, implement the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, in this right triangle ADC, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. It again, the right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus CD squared. AC is the missing side, so it is AD is B, therefore AD squared is B squared, plus CD squared. CD is C, therefore CD squared is C squared. So in total, according to equation 2, we should find out that AC squared equals to B squared plus C squared. So we have two different equations for AC squared. According to equation 1, AC squared equals to 2A squared, while according to this equation 2, AC squared equals to B squared plus C squared. Therefore, we created equation 3 that says that AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, while AC squared according to equation 2 equals to B squared plus C squared. So in total, according to equation 3, we should find out that 2A squared equals to B squared plus C squared. Here we divided this equation 3 by 2 and found out that A squared equals to B squared plus C squared over 2. It's given us the equation that the perimeter of this quadrangle ABCD equals to 18. So A plus A is 2A plus C plus B equals to 18. 2A plus B plus C equals to 18. According to equation 4, we found that 2A plus B plus C equals to 18. It is given as the question that the area of this quadrangle ABCD equals to 16 square inches in size. Quadrangle ABCD consists of those two right areas, and therefore the area of quadrangle ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of this second shape that it consists of, that is the area of this right triangle ADC. And again, the area of quadrangle ABCD equals to the area of the first shape that it consists of, that is the area of the right triangle ABC, plus the area of the second shape, that is the area of the right triangle ADC. The area of the right triangle ABC equals to the base, that is A times the height BC, that is A divided by 2, so it is A square over 2. The area of the ABC to the equals to A square over 2. So, plus the area of the second shape, that is the area of this right triangle ADC. The area of this right triangle ADC in total equals to the base BC times the height DC over 2, so it is BC over 2. The area of the right triangle ADC equals to BC over 2 square inches. So in total, we should find out that 16 equals to A square over 2 plus BC over 2. Here we multiply this equation with equation 5 by 2 and find out that 16 over 2 is 32 equals to A square over 2 times 2 is A square plus BC over 2 times 2, that is BC. So in total, 32 equals to A square plus BC, according to equation 5. And again, we should find out that according to equation 5, 32 equals to A square plus BC. According to equation 3, we should find out, we already found out that A square equals to B square plus C square over 2. So we can substitute A square in this equation 5 by B square plus C square over 2 from equation 3. We need it, we should find out that 32 equals to A square, that is B square plus C square over 2 plus BC. So today, according to equation 5, we should find out that 32 equals to B square plus C square over 2 plus BC. Here we multiply BC by 2 and then we divide it by 2 in order to confirm of this expression. We should find out in total that according to equation 5, 32 equals to B square plus C square over 2, and we have here BC times 2 over 2. That is 2 times BC over 2. So in total, according to equation 5, we should find out that 32 equals to B square plus C square plus 2 times B times C over 2. Here multiply this equation of equation 5 by 2 and find out that 32 times 2 is 64 equals to B square plus C square plus 2 times B times C. We have the algebraic identity that states that A square plus B square plus 2 times A times B equals to A plus B square. So we use this algebraic identity, and in order to find out what is the value of B square plus C square plus 2 times BC, actually according to this algebraic identity, B square plus C square plus 2 times B times C equals to B plus C square. It equals to 64. So in total, B plus C square equals to 64. Here we took out of this equation and found out that the square root of 64 is 8, and the square root of B plus C square is B plus C. So in total, according to equation 5, we found out that B plus C equals to 8. This is according to equation 5, but according to equation 4, we found out that 2A square equals to B, found out that according to equation 4, 2A plus B plus C equals to 18. So we can substitute B plus C in this equation 4 by 8 for this equation 5, because B plus C equals to 8. We did it, and actually found out that according to equation 4, 2A plus B plus C is 8 equals to 18. Here we substituted 8 for this equation 4, and we found out that 2A equals to 18 minus 8 is 10. So 2A equals to 10. So here we divided this equation 4 by 2, and we found out that A equals to 10 over 2, that is 5. So A equals to 5 minutes in itself. This is 5 B8, is equals to A, and A equals to 5. So B equals to 5, and BC is also equals to A equals to 5 units in its length. In the next step, we implemented the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem on this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, the right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so it is. So it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, AC squared equals to 25 plus 25, that is 50. So AC squared equals to 50, substitute 50 by 25 times 2, and find out that AC squared equals to 25 times 2. AC squared equals to 25 times 2. Here we took out of this equation and found out that AC equals to the square root of 25 is 5. So inside the root we have to with 2. So in total we found out that AC equals to 5 times square root of 2 units in its length. The diameter AC equals to 5 times square root of 2 units in its length. Therefore, the radius must be equal to the diameter over 2. The radius of this circle, that is the radius that you are looking for, must be equal to the diameter AC over 2. That is to say, it is 5 times square root of 2 over 2. So in total, we should find out that the radius that you are looking for this equation, that is the radius of this circle, is equal to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius R equals to 3.536 units in its length. So here is to repeat on the first question. The next step, repeat on the second question, or the second solution of the second question. In this second question, our task was to find out the length of this line segment AP that equals to x. So we have to find out the value of x. So in the drawing, we have a circle that is inscribed by this right triangle ABC. We know that QS equals to 25, chord QP equals to 24, and this is a tangent to the circle at this point. So SM is a tangent to the circle. Again, our task is to find out the length of this line segment AP that is equals to x. We have to find out the value of x. So in the first step, we implemented rule 2 in our drawing. Repeat rule 2, according to rule 2, the lengths of two tangents for a common center point to a circle are equal. So in the drawing, we have a circle. This is the common center point, point P. For this common center point, point P, we have two tangents to this circle. Tangent PA and tangent PB. And according to this rule, they are equal to each other. That is to say, the length of tangent PA is equals to the length of tangent PB. Or PA equals to PB. So we can actually implement rule 2 in our drawing. In our drawing, this is the common center point, point A. For this common center point, point A, we have two tangents to this circle. Tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP is x, therefore AQ must be also equal to x units in its length. We find the length of this short tangent VM as A. And we focus on this common center point, point B. For this common center point, point B, we have two tangents to this circle, tangent VM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to A, therefore BQ must be also equal to A units in its length. In the next step, we focus on this common center point, point S. For this common center point, point S, we have tangent SM, that is tangent to this circle, point M. Likewise, we have the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied and therefore we can implement here rule 10. Please click on rule 10. According to rule 10 is true in any circle. So if AB is any point in the circle and PT is tangent to the circle, then the following equation is true, that PT square equals to PA times PB. So in the following circle, this is connection point P. From this connection point P, we have tangent PT, that is tangent to the circle is point A. Likewise, we have the extended called PA, that is point P. So in this point, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So simply implement rule 10 in our drawing. Now drawing, to focus on this connection point S, we have tangent SM, that is tangent to this second point M. The extended is called PQ, touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true, that SM square equals to SQ times SP. Again, SM square equals to SQ times SP. Again, according to rule 10, SM square equals to SQ times SP. SM is the missing sign, so in it is SQ is 25, SP is 25 plus 24, that is 49. SQ is 25, SP is 49, so SM square equals to 25 times 49. Here we took out all the equation and found out that SM equals to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 35. So the length of this tangent SM is equals to 35 units. What is the length of SB? SB equals to SM minus BM. Again, SB equals to SM minus BM. So SB equals to SM, that is 35, minus BM, that is 8. So in total, SB equals to 35 minus units in itself. SM is a tangent. SM is a tangent, it is absolutely straight line. So if you focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line SM at point B? We have this angle that is right angle plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the next step, we implemented the Pythagoras theorem on this right triangle SQB. Only to the Pythagoras theorem, on this right triangle SQB, SQ square equals to QB square plus BS square. SQ square or QS square equals to QB square plus SB square. SQ is 25, therefore SQ square is 25 square, that is 625, and is equals to QB square. QB is 8, therefore QB square is 8 square, plus BS square. BS is 35 on the side, therefore BS square is 35 on the side square. So in total, we should find out that 625 equals to A square plus 35 on the side square. So here we have 625 equals to A square, and we have 35 on the side square. 35 on the side square equals to 35 square, that is 1225, plus A square, plus 2 times 35 times A is minus 78. So we have 625 equals to A square plus A square, that is 2A square, minus 78, plus 1225. Here we subtract 625 from this equation, and finally found out that 2A square minus 78 equals to, again, 625 equals to 2A square minus 78 plus 1225. So I'm subtracting here 625 from this equation. So here we're left with nothing, that is to say 0. And on the other side of the equation, we have 2A square minus 78, and 1225 minus 625 is 600. So in total, we should find out that 2A square minus 78 plus 600 equals to 0. Here we divided this equation by 2 and finally found out that 0 over 2 is 0, 2A square over 2 is A square, minus 78 over 2 is minus 45A, and 600 over 2 is 300. So in total, we found out that a squared minus 45a plus 300 equals to 0. This is the quadratic equation, and the general formula for the quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And if I know the value of x according to the following formula, x equals to minus b plus minus square root of 4 times ac over 2. And now, over 2a, of course. Again, the general formula for x, that is the variable that we're looking for, is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, and this will say a squared minus 45a plus 300 equals to 0. The variable that we are looking for is a. So x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 45, and the coefficient c equals to 300. The only thing that is left to do is to put this data of our specific quadratic equation inside this general formula for x, and this way we find out the variable that we are looking for in our specific quadratic equation, that is a. So we did it. We found out again x equals to a, so substitute x by a, and it is equals to minus b. b is minus 35, therefore minus b is minus 35, that is plus 35, plus minus square root of b squared. b is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a times c. A is 1, c is 300, so minus 4 times a times c is minus 4 times 300, that is minus 1200. So inside the root we have 1225 minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we have found that a equals to 35 plus minus square root of 1225 minus 1200 over 2. 1225 minus 1200 is 25. So in total, we actually found out that a equals to 35 plus minus square root of 25 over 2. The square root of 25 is 5. So in total, we should found out that a equals to 35 plus minus 5 over 2. So here we have two solutions to the possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20, while the second solution for a is that a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is 15, and the first solution for a is 20. So here we did a construction. First of all, the grand triangle AQP is an associated triangle because side AQ equals to side AP. QP is the base of this grand associated triangle AQP. So we need a construction, that is to say, from point A we do perpendicular on the base QP. Again, from point A we do perpendicular to the base QP of the associated triangle AQP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And you find the touching point of the perpendicular from point A and the base QP, this point is point Z. So again, Z is the perpendicular to the base QP. So here you can implement rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisect the base. ABC is an associated triangle because AB equals to AC in its length. BC is of course the base of this associated triangle, ABC. From point A we do perpendicular AO to the base BC. Again, from point A we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this rule 21, the perpendicular AO bisect the base BC. If AO bisect the base BC, it means that the first half is BO, the second half is OC, and each half of course, equals to BC over 2. So BO equals to OC equals to BC over 2. So you can implement all 21 in our drawing. Why? Because in our drawing, we have the associated triangle AQP, the perpendicular AZ, the bisect the base QP. That is to say, it divides the base QP into two halves. The first half QZ equals to the second half ZP, and each half must be equal to QP over 2, because QP has been bisected by the perpendicular Z. So QZ equals to ZP equals to QP over 2, according to rule 21, of course. According to rule 21, the first half QZ, of course, equals to the second half ZP, and each half equals to QP over 2. QP is 24, 24 over 2 is 12. From this equation, we derive that QZ equals to ZP equals to 12. QZ equals to 12, and ZP also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is alpha, the size of this angle must be also equal to alpha. So in the green right triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in this small green triangle SQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. This is the right green triangle AZQ, that is similar to this right triangle SQB. So while those two right green triangles are similar to each other. First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we found out that all the angles of this green small right triangle SQB are corresponding equal to all the angles of this green big triangle AQZ, and therefore those two right triangles are similar to each other according to angle similarity rule. So again, we found out that the right small triangle green QBS is similar to the right big triangle AQZ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SQ of this small right triangle SQB over side AQ of this big right triangle AQZ is equal to side QB of this small right triangle SQB over side ZQ of this big right triangle AQZ. Okay, again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side QS of the small right triangle SQB or side AQ of the big right triangle AQZ equals to side QB of the small right triangle QBS over side QZ of the big right triangle AQZ. SQ is 25, AQ is X, QB is A, and QZ is 12. So in total, we found out that 25 over X equals to A over 12. Here, of course, multiply this equation, and we found out that A times X equals to 25 times 12 is 300. So A times X equals to 300. Here we divided this equation by A, and we found out that X equals to 300 over A. So we have two solutions that are possible for A. A could be equal to either 15 or it could be equal also to 20. In order to find out what is the real solution for A, maybe those two solutions are both correct. It is also possible. So we have to check how many solutions for A we have, and maybe one of the solutions is not correct solution, and then we have only one solution that are possible for A. In order to find out how many solutions A have, I'll draw this right triangle with the circle that is described inside it in the new drawing, and we analyze the new drawing with the right triangle with the circle that is described inside it. So actually this is the right triangle ABC, and this is the circle that is described by this right triangle ABC that I got from the original drawing. We already found out that AQ equals to X and QB equals to A. We define the point of tendency of tangent BC with this circle. This point is point M. We define the center of this circle. This point is point O. We define the radius of this circle as R. We join points O and M together with a straight line. Point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of the circle. This is equals to R. The radius for M, this is equals to R. The radius for M is drawn to point M, that is the point of tendency BC with this circle. And whenever your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Point Q is the point of tendency of tangent AB with this circle. We join points O and Q together by straight line. OQ is of course the radius of the circle. This equals to R. According to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the small quadrangle OQBM, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in size, according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle OQBM, we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small lower rectangle OQBM, side OM must be equal to the opposite side QB. But OM is out, therefore the opposite side QB must be also equal to R, and it's in its length. So QB equals to A, and it is also equals to R. In the next step, we did a construction, that is to say we extended the reduce MO equals to R, we extended the reduce MO by a straight line until it touches the circle. We define the touching point of the extended reduce MO with this circle. This point is point Z. When you extend a straight line by straight line, the result must be a straight line. MO is a straight line. We extended the straight line MO by straight line, therefore the result MZ must be also a straight line. So if you focus on the right side of the straight line ZM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the right side of ZM at point O? We have this angle that is the right angle, plus this missing angle, so then the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in size. In the next step, we did a construction, that is to say, from side AB, we draw a tangent to the circle at point Z. Again, from side AB, we draw a tangent to the circle at point Z. We define the touching point of the tangent at point Z with AB. This point is point T. Repeat again, TZ is the tangent to the circle at point Z according to our construction. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle, that is equals to R. The radius of OZ is equals to R, the radius of OZ is drawn to point Z, that is the point of tendency of tangent Z with this circle. And whenever your radius is drawn to the point of tendency, then tangent, whenever your radius is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If tangent TZ is perpendicular to ZO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in total, in the upper quadrangle TZ or Q, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in its size. So in quadrangle TZ or Q, we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZ or Q, side ZO must be equal to the opposite side TQ, but ZO is out, therefore the opposite side TQ must be also equal to 1 unit in its length. So we already found out that QB equals to A and QB equals to R. Again, QB equals to A and QB also equals to R. What about AQ? AQ equals to X. But AQ also equals to AT plus TQ. So it is AT plus TQ. TQ is R, so in total AQ equals to AT plus R. Again, AQ equals to X, and AQ also equals to AT plus R. And again, AQ equals to X, and AQ also equals to AT plus R. AT is the length of this line segment, therefore it is absolutely a positive number. The length must be a positive number. Therefore, AT plus R is definitely greater than R, because AT is a positive number. Okay? And from this inequality, from this long inequality, we derive that X is greater than A. Again, X is greater than A. X is greater than A. Found out that X is greater than A. So we have two solutions that are possible for A. A could be equal to either 15 or 20. We already found out that X equals to 300 over A. X equals to 300 over A. So if A equals to 15, it means that X equals to 300 over 15. This is 20. So if A equals to 15, then X equals to 20. Likewise, if A equals to 20, it means that X must equal to 300 over 20, that is 15. So the conclusion for now that if A equals to 20, then X must be equal to 15, and if A equals to 15, then X must be equal to 20. So F in this option, that A equals to 20, then X equals to 15. 15 is definitely less than 20. We have here 20 equals to A, so can write here that 20 equals to A. And from this inequality, we will derive that X is less than A. X is less than A. It contradicts our previous findings that X must be equal to, X must be greater than A. If X must be greater than A, X cannot be less than A. Due to this contradiction, we cancel the solution. A can never be equal to 20. We take into account only the other solution, that A equals to 15. Yeah. So if A equals to 15, 15 is definitely less than 20, that equals to X. Again, 20 equals to X. 20 equals to X. You can write here that 20 equals to X. And from this inequality, we derive that X is greater than A. X is greater than A. Exactly like our previous findings that X must be greater than A. It is not contradicts our previous findings. Therefore, the solution to this question is that X equals to A. AP is equals to X. AP is equals to X is equal to 20 units in itself. X equals to 20. AP is equals to X is equal to 20 units in itself. And again, this is line segment AP, that equals to X, and X is equals to 20 units in its length. Okay, thank you very much.